But I want to start by just saying that one of the things that I did is I took the AC project from lab and I moved it last. And to be completely honest with you, I feel that the importance of that particular project is not nearly as important as the magneto, the generator, the alternator. Because the things that you'll do in the AC project just aren't necessarily applicable to your day-to-day life as an A&P. Maybe it will be for some of you. But I say that and I give you that information to tell you that that is, to me, not an important project. So if we got to the end of the class and it was you have to rush to get something done, that's the thing that I would prefer rather than the other important stuff. But if you personally choose that you would rather do the AC project instead of moving into the magneto project, I'm okay with that. Let me tell you the reason why you might want to is because the magneto project's a rather difficult project. You're expected to know a lot for the oral. It's very intensive, and it's going to be your first oral for a lot of you. So it's like, oh, and it's a shocker. It's like, wow, okay. And that's the way the orals will go for the rest of the program for you. So for some of you, you may struggle a lot until I get to the magneto oral, which won't be for another 2 weeks. And I can't do that one until I do the next two because those two tie into that one. So that hopefully that made sense to you because it was supposed to. So recap, what's the headline there? We moved the AC project to last, but if you really want to do it first, you can.
Okay, so then what about because I think logic gates is right after AC.
Oh, you do logic gates first.
So do logic gates still. Okay, cool.
All right, so this week we're going to talk about alternating current, AC, and we're going to do quite a bit of math. But historically speaking, it's another one of those things where people either get an A or they're just completely lost. And most everybody gets an A. And so far, you guys have been kind of ahead of the curve on a lot of things. So I have high hopes. So let's get into it because it's a lot to cover this week. So one, we're going to talk about AC.
One more thing before we get
That is the other, huh?
Can we get
I pushed the bot in. AC is the other half of the group, DC. So AC, which stands for alternating current. And I'm really going to need you guys to be brave and raise your hand if you don't understand something. Alternating current theory, AC theory. So what is AC? AC is current that periodically changes direction, and continuously. So periodically changes direction. It means it's not constantly changing direction. It's going to do it every now and then, a cycle. So it goes up, which is not changing direction, and then it goes down and crosses a line and changes direction and goes the other way. But it is continuously changing in amplitude. Meaning you take your 6-volt battery, 12-volt battery, whatever battery you happen to have, and you measure the voltage, and it is 6 volts. And you could come back in an hour, and it's about 6 volts. And you can come back in a couple days, and it's about 6 volts. Unless you put a big load on it. But it's pretty much stays about the same with the battery until it slowly starts going off to zero, but it never changes direction, and it's not continuously changing. But AC is. So that is, I'm not going to write it, as opposed to DC that never changes direction and it never changes amplitude or magnitude. So true DC, which stands for direct current, is only, that's true DC, is only created with a battery. In a little bit, we're going to talk about how to create DC out of AC, but we talk about oscilloscopes, and oscilloscopes is a TV. Yeah, go TV, let's watch TV. Yeah. A TV that shows you a picture of what the electricity you're looking at. So if we actually hooked up an oscilloscope and we looked at a picture of your battery DC, it would be a very, very straight line, and you could zoom all the way in, still be a line. But you could take something that creates DC out of AC, and if you zoom way out, it'll look like a straight line. And when you zoom in, pretty soon you'll see that it's not. It's got a wave pattern to it. So that's not true DC. So we have, how do we get DC then?
From a battery.
Battery. Well, I don't want to write this, but if I don't, I'll screw up my whole timeline. All other electricity produced with mechanical means is AC converted to DC. I don't love what I wrote there. So what I'm basically saying is you have true DC, which is made by a battery, and then everything else starts out AC. You got your alternator in your car, your airplane, that's AC, made into DC. You got a generator, it's AC, made into DC. Got a power plant, starts AC, stays AC. So everything really is AC, with the exception of battery, everything is AC converted to DC. So that's why AC is kind of important, because everything really starts there except for the battery. So all electricity produced, let's see, with mechanical means, is AC converted to DC. All right, so and now we have airplanes, and the more modern aircraft, especially the large aircraft, not so much the small ones at all, but large aircraft, they're going to AC. They're getting rid of as much DC as they can, because AC has a lot of advantages over DC. Anybody ever watched that movie about, I watched it on the plane coming home from Boston. I forget the name of it, but it had it was during the time when they were bringing electricity to America. That Nikola Tesla and Edison and Westinghouse. And anybody watch that?
I think I've seen it.
It's actually really good. Do you remember the name of it? Something Current or something. I don't know. But it's actually, it's a movie. I don't know how accurate it is, but it's really good. And it talks about the fight between bringing electricity into America, whether they were going to go DC or AC, and how much dangerous the DC actually was. There was this fight between it and all that kind of stuff. And it's how they invented the electric chair to kind of prove that, one was bad and that was good. It's very political too. So AC has advantages. Okay, so number one, voltage.
Excuse me, is it called a current war?
Yeah, that's it.
Yeah, that's
Current war.
Sounds about to ask too. It's called the current war.
Oh, you're my guy. I had one student one time. He had everything I said he Googled. I just go, what did Google? Everything. Doesn't matter what I was talking about, what Google just said. He'd tell me. He Googled every sentence I wrote, everything. He was like my fact checker, man. He was just looking. He was a good guy. Voltage can easily be changed. So if we want more voltage, you can get it. You want less voltage, you can get it. You can step it up, step it down. Easily be changed by transformers. Talk about transformers next week. What else I got here? AC can be produced. AC can be produced in three-phase systems. allowing the use of smaller motors. So in other words, go three-phase AC. I'll talk about what that is a little bit more in a page or so. Yep. So you can make the motor smaller. Well, smaller motors in aviation is a good thing. Because one of the things we haven't talked about, especially when we talk about large aircraft, is revenue. And, you know, it's all about how many butts you can get in a seat, how much luggage you can carry or baggage or revenue down below, the least amount of fuel, which means less weight. So less weight you have in the aircraft, the more profitable it is. AC generators. Are more efficient. That is a generator that starts with AC and makes AC. More efficient than DC generators. And a DC generator, which is a generator that makes AC and then converts it to DC. The wire used in AC is much smaller than DC. Well, I'm glad you asked. Than DC. Let's take an example. You can say, I wish I would have asked, but it's here anyway. So, a 1 horsepower motor. Now you already saw you asked. Motor. That'd be 746 watts, 60% efficient. Efficient. Driven at a distance of 100 feet. So 100 feet from source, 100 feet from source. Let's see, driven at a distance of 100 feet from source. Source voltage of 10 volts. Why 10 volts? I don't know. I've obviously got this off of something. We'll need 125 amps. And if we look at our chart in 4313, we said, okay, 125 amps, distance 100 feet. We follow down, we get to the wire. We are going to need we'll need a number 1 wire. A big wire is correct. So number 1 wire. And that will weigh 25 pounds. That's 25 pounds of wire. So, all right. Let's see. If we used AC, so 200 volts AC, we'll need 5 amps instead of 125, which uses a number 18 wire. A number 18 wire is the wire that you have pretty much for your little alligator clips, right about that size. That weighs 1 pound. 1 pound. That's one item in the aircraft. So that is a good thing. Oh, I see where I'm going with this. All right, let's take a look at this. This is kind of fun. There we go. Nope. Nope. We're going to talk about alternating current. Is there a video down there or something? Oh, yeah. All right. Alternating current, which is what we're talking about. And as I had mentioned, alternating current is constantly what?
Direction.
Nope. Constantly doing one thing.
Constantly changing.
Amplitude. See, it's always going up or it's always going down. It's never still. And periodically, direction. So this line right here, this black line, would represent 0 volts. So then positive, then negative, then positive, negative. So in other words, if you had a voltmeter and you were kind of measuring it, you know, like this side, this is positive, this is negative. Well, then it's this way, then it's this way, then it's that way, then it's this way, then it's that way, then it's this way. So you got to change real quick when you use the meter. All right, so why AC? Where do we get AC? That should be the next. All right, so you might want to take some notes, since I'm not going to write all this stuff down. Where am I over here? Yep, I'm not going to write all this down, so I'll let you write it down. Voltage induced in a conductor. How is voltage used in a conductor? Well, we need 3 things to generate current flow. Unless one of those things is a battery, then you only need 1 thing. But assuming we don't have a battery, that was a joke. Assuming we don't have a battery, we got 3 things to make electricity. Those 3 things are you caught up? You good? You're my guy.
Yes.
All right.
Gotcha.
Yeah. A magnetic field. Time myself. M-A-G-N-E-T-I-C-F-I-E-L-D. Okay, I wrote magnetic field. It's got to have a magnetic field. Where do we get a magnetic field from? A magnet. Okay, that's good. Magnet is correct. Need a magnetic field. 2, you got to have a conductor. Conductor is a... All right, so you got to have a magnetic field, you got to have a conductor. You have a magnetic field, you got a conductor, then you need relative motion. I have a toy. This is literally nothing more than wire. I made it in the garage. Just stuff laying around the garage. I make kids tinker toy. Got a nail. I just took some magnets and I put them on the nail and I taped them together. So I got 2 magnets in there, 2 bar magnets. And then I took this wire and I wrapped the wire around it a bunch of times. So I need 3 things. They are magnets, conductor, and still works. Yay, still works. See the light bulb? So, there you go. I got shocked. No, I was kidding. So, I did not. But yeah, that's all you need, right? So, magnetic field, conductor, relative motion. So, whenever you run a magnet across a wire, you are going to get electricity, right? And the more turns that I put on there, the slower I would turn it or have to turn it, or the faster I turn it, the more I'm going to get. So, all right, but obviously this little thing that I have here is not practical because who wants to sit there and go like this all day with a little wire, right? That wouldn't work. So you want to change it into some sort of rotary motion. So, yes, problems. Well, that's not very practical to do that. My arm got tired the way it was. So the solution, how do we create electricity doing something like this? Is we're going to loop the wire. Now, I did a little bit different. I've got a stationary wire and a rotating magnet, but I suppose that if I put it all together and I held it like this and spun it this way, it would, be the opposite, but I'll break it. Okay, so we're going to create this. So that loop of wire is called an armature. Follow? And we have brushes and rings. Can everybody see up there, or is it easier if I point here? All right, so we've got the armature, which is this loop of wire, and then we have these rings. These are the rings, thing that look like a circle or a ring, and then this little flat piece right there is a carbon brush. So it stays still and it rubs against the ring, and the ring goes around the carbon brush, and then we've got a load across there, because you always have to have a load, right? All right, so take note that in this loop, the top of the loop is attached to this ring right there. So it's the topmost ring, and then the bottom of the loop is coming around, and it's on the back ring right over here. Follow? All right, hang on, we got a problem here. So one of the problems is, oh, she can't do that. Sorry. I was going to say, you can't really see it if you're watching online, but I'll try and remember to make it so you can. What was that again? Slideshow. Okay. All right, so we have the brushes and the rings, and we rotate this. Everybody's with me so far? Okay, this is one of these weeks where you got to, I mean, if you're not there, don't, it's so bad if you come back to me 10 minutes later and go, I don't understand. All right, so if we take and we rotate this, we are going to get relative movement through a magnetic field. Follow so far? All right. So we rotate that, it's going to work out just fine. Let me see. What are the problems? Well, there are many, but primarily this will produce AC. This actually is a PowerPoint that I use to show you how a generator works that makes DC, but I want to use the beginning of it to show you how AC is created. So this is AC. But what is AC? Well, we take a look at it just a little bit different with this rotating loop and stuff. And we take a look at magnets. We have the greatest amount of magnetic flux. Magnetic flux is a word we're going to use a lot now. And it's that invisible lines of force that are created between magnets, between the north and south pole of a magnet. Externally, you can actually, with a north and a south, they'll go through the air. If it's a bar magnet, north-south, they're internal, and then it'll come out and around later. We'll talk about magnets a lot later. Okay, so the greatest voltage occurs as a conductor passes at right angle to the flux, which is to say that as this armature is sideways in this picture, it's going right through here, and it's really cutting through those lines of flux. Right, that's the word we use, cutting through the lines of flux. It's going straight down. Well, but as that armature starts to go up and around, and it starts to become, well, when it gets up here, which I think is the next slide, it's totally parallel to the lines of flux. So instead of cutting through the line of flux, it runs this way. And you get absolutely no voltage, right? Because you're not cutting through the lines of flux. Follow? Right. So not cutting through the lines of flux. So how much voltage would you get? None. A wire that is not cutting through lines of flux is
0 volts.
0 volts. So now we have 0 voltage. So I guess we can do this. It's kind of fun. So determining the direction of current, the left-hand rule. So motion, thumb points in direction of motion. The pointer field points in the direction of field from north to south. The way I remember how magnetic lines of flux go, is it from north to south, south to north, is I think of the globe, which has a magnet inside of it because of the North Pole and the South Pole. Right? Those are magnetic lines of flux that surround the Earth. And so that's how a compass works, is just aligns with the bar magnet that's in the Earth, so to speak. And the lines of flux on the globe would start at the top and fall down to the bottom. So I go, okay, it goes from north to south because they fall down. That's what they say. I don't know who they are. All right, so got to use your left hand. Thumb points in direction of motion, pointer in the direction of the field, and then the middle points to the direction of current flow. That would be electron negative to positive. So now that, okay, you guys can do this with your left hand. This will be our gang sign now. Okay, so we're like, yell now. To the ohm, right? What was that? You have to say ohm too.
Yeah, to the ohm.
To the ohm, yeah. All right. So left hand rule. This one's kind of hard because, so I'll do it. So which way would the current flow? So thumb is?
Direction of movement.
Direction of movement. All right. So it's going up and down. Current flow from?
North to south.
North to south. So boom, which way is the current going to flow?
Toward this.
Out of the board. There we go. Out of the board. You guys got it. All right. Not that that is so important, but when we take and put that all together, okay, remember the little loop that we had right here? And we're going to go ahead and move this around. And we're going to think about that using our rule of thumb here, and we're going to do that. Loop A is going up. So if loop A is going, loop A, loop A, not loop A. Loop A is going up, and we have, north to south is this way now. I knew there was going to be a problem somewhere. North to south is that way, but which way do we have the current flowing? Well, it's going to show you, so I don't have to do too many contortions. But this is why the current is now flowing this way and coming out this way and going through the load that way. You follow?
Yeah.
Okay, just trust me on that. So in this way, left-hand rule of thumb, line it all up, north, south, east, west. Current's going to come out of here and go through the load, right through that, out this way, through there. But in a little bit, notice that loop A is over on this side and loop B is over there, right? Okay, so now we're going to switch it around. We just moved it. Follow? See what I did? I'll go back. A, B, now it's BA. So A is over here, B is over there. So when it did that, the rule of thumb, north, south, east, west, it went different because A is going, was A going up? Whichever way A is going, it made it so that before the current was flowing this way, now because A is over here, it's got to go the other way. Because it's going up, then it's going down, then it's going up, then it's going down. So see, it's, one way is this way, then it goes down, it's got to go that way. So current's got to go back and forth and back and forth. That's the point I'm trying to make. So now we got AC. That's how we get AC. So again, applying the left-hand rule of thumb, the reversal of current flow produces alternating current. Back, forth, back and forth. You didn't learn anything. So we put all of this together and we look at it. We can see that when the loop is straight up and down in this case, and it's going parallel, P word, going parallel to the lines of flux, we have how much current? Zero. And that's reflected right here at point 0. Let's see. Okay. We have 0 current, 0 volts too. All right, because we could talk voltage or current. It's voltage and current are going to both do this kind of thing. All right, so then the loop comes around, and right in the middle, it's cutting through the densest lines of flux, because the lines of flux tend to move towards the middle of that magnet. So right there, it's the most dense, and that loop is going perfectly parallel. So we get the maximum amount right there. And that was 90 degrees later, right? Because it went 0, 90. Then we're going to come around again to 0. So it comes around to 0. And of course, we have how many volts current? We have 0. Okay, then it keeps going around one more time. And then we're going to get a peak, but it's the opposite. It was this way, then that way, then this way, then that way. All right? So you can see right here by the arrow, right now it's going that way, and a little bit it's going to go that way. So positive, negative, positive, negative. And then a little bit it's going to come around and go to 0 and start all over again. So there's AC. That's right, that's vector. Because later we're going to talk about vector. So we might as well talk about vector right now. Oh, man. Because I like vector. We have to turn on the sound.
Hey.
I'm applying for a new film loan. Go by the name of Vector. It's a mathematical term. Quantity represented by an arrow with both direction and magnitude.
That's the point I was trying to make.
Vector! That's me.
The vector is something that has...
Vector! That's me.
Oh, yeah. Went too far back.
Vector! That's me. I'm committing crimes with both direction and magnitude. Oh, yeah!
If everybody gets an A on the test, I will do that. Oh, yeah.
The whole scene?
Yes. I'll even wear the jumpsuit if you buy it for me.
If you buy it.
I don't have it. All right, so we went through, let's see, point point number 2. Point number 2 is, how is AC produced? How is AC produced? And we just went through it. What 3 things do you need?
Magnetic field, conductor.
Relative. All right, so the takeaway that I need you to know right now is that why does AC go up and down, and why does it change direction? And hopefully that explained it, because when we come back around, well, you're going to need that. That's really important right now. All right, so we're talking about that. We'll talk about now waveforms.
Kevin,
Yeah.
does AC not need a return to ground if it's just going?
There is okay, remember in DC, ground is really a return path,
Right, so it doesn't need a return first because it's just.
but you need 2 wires. Because you have technically speaking, you would have a positive and a negative. It's just they switch. But you still have to have a path all the way through.
To the generator or motor?
Yeah.
Okay.
Well, so if we were to take apart the light switch over there, there'd be 2 wires. There'd be a black and a white. And a green. But that's a whole other thing. That's a safety wire.
You have
And
to have a closed circuit.
what's that?
You always have to have a closed circuit.
Yeah, closed circuit.
I don't understand how the loop is made from where power is generated. Is it that loop that we were looking at?
Well, if we were to, no, not necessarily. That loop is self-contained inside of a machine, and then the machine would look just like this, an alternator or generator. It's going to have a lead off the top and a lead off the bottom. And that's going to go, and it's going to go through our load. We'll make it a light and go this way. And so for just a brief second, a moment, it's going to go this way. And this is going to be positive, and this is going to be negative. And then for a brief second, it's going to turn around. This is going to be negative, and that's going to be positive. So literally, the electrons are flowing this way, then they turn around and go back the other way. Then they go this way, then turn back around and go the other way. So believe it or not, these lights, and so you'd think, well, that's going to flicker, right? These lights are flickering. They're flickering at a rate of 60 times per second. And if you were to take a handheld tack checker that checks the tachometer of a propeller, which works by holding it behind the propeller, and the propeller is going around, and this thing catches the flickers of the prop. If you held it up to here, it's how you calibrate it. So, yeah, they're just flickering. And actually, I think they had to work on that, how much they could flicker before it made us sick, and where it would work, and we don't notice it. So, yeah, it goes back and forth, back and forth. You always have to have 2 wires. I suppose technically we could do something like this. Probably shouldn't, but, if we did that, that looks familiar to you, right? Well, it's going to do the same thing. It's going to go around this way, and then back up through the ground and out, and then it's going to go this way. Back up the ground. So it's just going to go back and forth, back and forth. But we don't do that.
When the alternator charges the battery?
You can't charge a DC. You can't charge a battery with AC.
Oh, okay.
We're talking AC now.
Okay.
Now, in a few weeks, we're going to talk about. Try not to sneeze. We're going to talk about how we take and convert that generator to DC. But for now, we're going to just stop and go. Okay, we've made an AC generator that produces AC, and there it is. But of course, there's so much wrong with where we stopped. Number one, that is an AC producing item. Number two, we talk about the waveform and how many seconds it is, how many waves you get in a second. Well, if you think about it, that one we just did, the slower I spin it, the lower the voltage is going to be, because voltage is dependent on how fast you spin something. So if I spinned it slow, there would be not much voltage. You can't even see the light up. But if I spin it fast, you see the light going. So spin it fast, you get more voltage. But the faster you spin it, the closer those waveforms are going to be to each other. And the slower I do it, the more they're going to spread out. So that creates some other problems. So many waveforms. We'll talk about different waveforms. So there's many types of waveforms. Many types. And again, this is what we would see on an oscilloscope. So we have DC, which is direct current, and DC is straight. So if I could draw straight, it would be straight, but it would just look like that, straight, but straighter. We could have something that is called chopped DC. Chopped DC, or a square wave. And this is one of the test patterns that the oscilloscopes that we have will put out. And it will look like this. Like that. Where this might be 0 volts right there. And this, well, on our tests, that would be 2 volts. Or you could even see something that goes up and down below and then back up and over. Oops, I go back down. Over, up, over. Where this is 0. And then, of course, we're talking about AC, which is also called sinusoidal. Sinusoidal. Just like I wrote it. just like it sounds. All right, so we've just looked at that, where we would see it go up, and then down, and then up, and then back down. And this could be my 0 volts right here, so everything above this line right here would be positive, and it swings negative down below. And when you're looking at an oscilloscope has grid lines on it, just similar to what I kind of have, so grid lines. Just like that, so squares. And you would adjust the dial, much like you would adjust a Simpson meter, so that each one of these radicals would equal something. Like this could equal 100. Well, if that's 100, then this is 100 down this way. So we would say the peak voltage is a little over 100. And it should be the same on the bottom side too, if you have the oscilloscope centered correctly. And so you would adjust that. They also have little half dashes in there too. 2, 4, 6, 8, 10. Yeah, little half dashes. So that's the project that we're kind of putting off the back burner, is really how to read this, which is not difficult. If you can read a Simpson meter, this is not hard. And in the same way, you'll do time this way. So up and down would be volts or current. Volts or current, whatever you set it for. By the way, volts are always measured in parallel. And current is measured in series. Yeah, okay. And then this way, back and forth, is time. So unlike the Simpson meter, we didn't care about time. Now we have to care about time when we talk about AC, because we want to know how far it is between waveforms, like from exact points, from this point to this point, or this point to, well, I'll be half wave back over to here, the peak to peak. Or I like to do it from the center to the center. So right there is one period right there. Period of time. All right, I'm going to write more about that here, so we'll move on. All right, so many types have B, 1 cycle of AC. 1 cycle of AC is from 0 volts to a maximum, to a max in one direction. Returns to 0. Turns to a maximum, to a max in other direction. And returns back to 0 and returns to 0 volts. So what I say, one cycle of AC is from 0 volts, which we have right there in the red, 0 volts right there, to a max in one direction. Here's my maximum right here in one direction. Returns to 0. Here's 0 again. Returns to a max in the other direction. There's my max in the other direction. And back to 0 in the other direction. Right there. That is called one cycle. And if we follow suit with that, with what we just learned, we can look at some other things as far as degrees go. So, here we go. This would be 0 degrees. We have a peak at 90 degrees. And now think about what we're talking about with that armature going around. So it's right here. And then it turns how many degrees? 90. And we got a peak. Now it's going to turn another 90. And we're going to go back to 0, which is, well, if I drew this right, it would be 180 degrees. So that really should be, sorry. Wasn't thinking I was going to do all this together here. So. All right, let's do it right here. So we got 0, peak, 0, peak, 0. So right here is 0 degrees. Right here is 90 degrees. Back to 0 is 180 degrees. To a max here, which would be 270. I love when you guys are yelling out answers. I don't have to think. And this is 360 or back to 0 degrees. And that completes one wave cycle. Now the number, or how many of these cycles per second, C, senor, the number of these cycles per second is the frequency. Is the frequency. Heard the song, you know, what's the frequency, Kenneth? That's what they're talking about right there. That's REM, right? You guys don't know. It's an REM song. You know, what's the frequency, Kenneth? Okay. Also called hertz. Oops. Also called hertz. Hertz. Or Hz, hertz. 1 hertz is 1 cycle in 1 second. Standard US, that's United States, electricity is how many hertz? 60 hertz. 60 Hz, 60 hertz. Which is, then how long is 1 cycle? That's 60 hertz, which is the same as 60 cycles in 1 second. So 1 cycle then is how long? It's 1/60, yep, of a second. Common aircraft. frequency, common aircraft frequency is 360. Well, I'm sorry. If I follow my notes, it's common is 400 hertz, but it ranges from 360 hertz up to 800 hertz.
The range.
Yep, range. One cycle may also be referred to as, may also be called a wavelength. So one wavelength.
Is there a guy that we named that after?
Hertz. He's also the guy who invented car rental.
Mr. Hertz.
He's, I was going to make an O.J. Simpson joke, but nobody would get that.
Don't do it.
Because he was the spokesman for Hertz. Let's see, wavelength. Amplitude. Amplitude is the peak value. That's how high it went before it went off, down the other way. So we have amplitude, we have peak to peak. Peak to peak is the value of peak times 2. So if I look back up here at this chart right here, I would say the peak, okay, here's my 0 line. So from here to here, that's peak. And then here's my 0 line. So from here all the way up there to all the way down there, that is peak to peak. Alteration, term that I don't actually use, is one half of a wavelength. So from 0 up to 0 or 0 down back around to 0.
Could you show us on the picture above?
So it's half. So if if this is an example from here to here is one wavelength, then 1/2 of a wavelength is the alteration. Well, that color didn't actually stick. There we go. Right there to the 0. If I said I had a peak voltage of 120 volts, what's my peak to peak?
240.
All right, because it's times 2. And let me see, last point here before break. We'll make it in black. There we go. The component. The component being installed. So in other words, you're installing a component on an aircraft, must be rated for the frequency used. Unless it's, I believe the brand new aircraft are going to some sort of components that are actually polyphase. They can handle a range of frequencies. But otherwise, it's the component is rated for a specific frequency. You got to use that frequency. So, all right.